All right, so our set of notes today is bonding basics, ionic, covalent, and metallic bonding. You will find a set of notes for these in Schoology that you can use or take your own notes. All right, so before we can understand bonding, we do have some other concepts that we need to go through. The first one is valence electrons, second is Lewis dot, and third is the octet rule. Okay, so valence electrons, again, are the electrons responsible for bonding. They're the electrons in the outermost occupied shell. All right. Because of electron configurations, the way electron configurations work, this means exclusively the s and the p electrons in that outermost energy level. The number of valence electrons also happens to be the same as the group number for s and p block elements. Doesn't work for d block elements or f block elements. But let's go ahead and take a look. Okay, so the full electron configuration for gallium is listed here. And we want to find the s and the p electrons in the outermost occupied shell. So the outermost occupied shell here is 4. The s electrons are 2. The p electrons are 1. And so this would have 3 valence electrons. Titanium, the outermost occupied shell, is 4. And there is no p electrons there, but there are 2 electrons. So titanium would have 2 valence electrons. All right, so once we know the valence electrons for a particular element, we can talk about Lewis dot diagrams. These are a representation of the valence electrons. They're usually useful for visualizing bonding. And basically what you do is you take the symbol and you add some dots for the number of valence electrons, which follows Hund's rule, sort of, where you're filling things in and putting 1 into each orbital before you put 2 into any. So for example, if I'm looking at nitrogen, nitrogen has 5 valence electrons. So 1, 2, 3, 4, 5. You put 1 on each side before you put 2 on any sides as things roll along there. Okay. So again, number of valence electrons, and then you just take the symbol and put the valence dots around that. This brings us to the octet rule. The octet rule is simply when atoms bond, they have a tendency to gain, lose, or share electrons such that they have 8 valence electrons. Okay. In other words, as we've discussed with electron configuration before, having a full subshell is a stable situation. So having full s and p subshells would give us a stable situation. S's have 2, p's have 6, add those together, and you end up with 8 valence electrons. Helium and hydrogen, those are good with only 2 valence electrons, and again, because they're in that first energy level, and the first energy level only has 2 valence electrons possible. Sodium has 1 valence electron, and it tends to lose 1 electron in bonding. How does that obey the octet rule? Sometimes think. Well, again, when metals lose electrons, where are they losing the electron from? They're losing it from the outermost energy. And so as a result of that, you end up with an electron configuration that now has 8 valence electrons in it. And voila, you are now obeying the octet rule. All right, so first major kind of bond is an ionic bond. And so just want you to take a moment, pause without looking at your notes, and say, what are all of the things that you know about ionic bond? Say them out loud to yourself, and then come back to the video. All right, so here are the things that you may have talked about. Ionic bonding typically happens between metals with nonmetals. The metal tends to lose an electron because it has a low ionization energy. The nonmetal tends to gain an electron because it has a high electron affinity, leading to electron transfer. This helps us form cations, which are positive, and anions, right, which are negative. Those opposites attract to make a bond, and when they do that, they form an ionic compound, which typically is crystalline in form. The simplest unit of an ionic compound is a formula unit, and they have these properties. They tend to be hard, brittle, cleave along crystal planes, have a high melting point and boiling point, conduct electricity as a liquid, or when dissolved. Okay, we'll get more into this in future units when we talk about, and into the properties in future units when we talk about different types of solids. Same exercise for covalent bonding. What do you know about covalent bonding? Come back to the video once you've got some ideas. Here are some things that you might have said. Covalent bonds occur between nonmetals. happens due to the mutual attraction of nuclei for electrons. This is what we mean by electron sharing, or opposites attracting to make a bond. A bit more about that in a second. They create molecules, and they can be solids, liquids, or gases at room temperature because it's IMFs that hold them together and not the bond itself. So again, what do we mean by sharing electrons? Well, we mean that there are several different electrostatic attractions in these bonds. There's attraction between the electrons and the nuclei, right? So the nuclei and the shared electrons, they attract one another. Okay. There's repulsions between the electrons. They push each other apart. And there's also repulsions between the nuclei. Okay. So in a covalent bond, these attractions between the nuclei and the shared electrons are stronger than the repulsions, and so this holds the bond together. The last kind of bonding that we have is metallic bonding. This happens in substances where all the elements are metals, because in nonmetals and metalloids, atoms generally bond to each other covalently, but in metals, we have a relative lack of valence electrons. Not very many valence electrons in metals, and so they tend to lose those electrons in order to become more stable. When they lose electrons, we form positive ions. Since there are no nonmetal atoms to pick up those electrons that get lost, we end up with two parts. We end up with a sea of electrons that are moving about, and we end up with metal cations in that sea. Those metal cations mutually attract the sea of moving electrons. So, for example, this cation attracts that electron, so does this one. So they're both grabbing at it at the same time. This connects the metal cations through the electron. However, those bonds are temporary. They form and fall apart rapidly as the electrons keep moving through the sea. However, the bonds at any one time in the structure hold the whole thing together. So therefore, we can think of a metal as a group of cations suspended in a sea of electrons, which we oftentimes refer to that sea of electrons as delocalized electrons. And the reason for that, why, is because this electron doesn't belong to any of the cations. It is used by the cations to hold the structure together, but it does not belong to any of them. It is delocalized. It has the ability to move throughout the sea.